This video is intended to walk us through the first part of the numerical descriptions of data. So let me go and click on here, and we're going to start with measures of center. And our goal here is to attempt to locate the center of a distribution. The idea is we've collected some data. We have ages, we have GPAs, we have some variable out there, quantitative measure that we're working with, and there are different ways to describe data. Previously we've looked at some graphs. We've looked at bar graphs, we've looked at stem and leaf displays, ways to get a feel for the shape of the data as it falls. Well, now we're looking at the numerical descriptions. We're looking at numbers that describe numbers. We have collected maybe 300 GPAs, and the first group that we want to talk about are measures of center. Where's the middle? Where's the center of that data set? And there are several different ways that we can do this. And so I'm going to click, and you see that the first way is the mean. And most of you guys are pretty aware of these measures of center. We have the mean, which is the arithmetic average. So if you add up the observations and divide by the total number of things you added up, you're going to get the mean. And there's a couple different formulas that I'm going to present to you here. We've previously looked at the summation sign. And so now we're thinking of mu, a population mean. You add up all the x's in the population, you divide by n, which is the population size. Now I'm going to give you a place for the symbols. You see it in your notes in just a second. But that's the first measure of center, the population mean. If we're working with a sample, which we typically are, then we use the symbol x bar. X bar is the average of the sample, mu is the average of the mean, and we've talked about in class already how x is a symbol that we use for individual observation. So your GPA is X. We go out and we collect a sample of, say, 200 students. We add the 200 together. We figure out an X bar, and then we use the X bar value to estimate a population mean mu. And so that's kind of how we're going to do it this semester. The mean is the most popular, and we're going to talk about whether it's the best in a second, but it is definitely the most popular measure of center. The second measure of center that we want to work with is the median. And the median is just typically the point that's in the middle of the ordered data. So whether you order the data from high to low, from low to high, it really doesn't matter. The median is going to be the one that's in the middle. If you have an even numbered of observations, so say they have 10 observations, or 100 observations, or 300, doesn't matter, whatever the even number is, there's not just one value that's in the middle. There's two values that are in the middle of an even numbered or an even number of observations. And so the median is found typically by just taking the average of those middle two. And so it's either the middle one observation or the average of the middle two. But either way, we think of it as the middle of the ordered data. And we have two different symbols that we use for medians. If we're working with a population median, we have this, what looks like an N gone bad. It's the Greek letter eta, which isn't really all that important. We're not going to see that symbol all that much. Mu and x bar we see the entire semester, but eta we won't see very much. And m is one of the symbols that's used for the sample median. That's the one that we're going to use this semester. Depending what text you look at, the sample median's all over the map. Different texts use different symbols for that, but neither of these symbols is as important as x bar and mu. Unfortunately, x bar and mu are pretty universal. Those are the symbols that pretty much everybody uses. And then the third measure, and this shouldn't be 1 and 2, this should be 2 and 3. The first one was the mean, the second one is the median, and the third one is the mode. And the mode is the observation or observations that occur most often. And so you just take a look to see which is the most prevalent, most common, most frequent observation, and that's the mode. How little respect the mode gets, it doesn't even have a symbol. I can't tell you what the population mode or the sample mode symbols are because they don't exist. And it's primarily because we don't use the mode all that much. Now the question that comes out of this discussion, we have three measures of center. Which measures best? And one way of answering this question is going to be dependent upon what do you mean by center. If you're thinking about the average, then obviously the mean is best. If you're thinking about which one's in the middle, well, median. If someone were thinking about which one occurs most often in the mode. But typically, when we're asking this question, which measure is best, what value do you think describes where the center of the distribution is? And you're probably thinking mean, median right now, because I said the mode isn't used all that much. But this is how I'm going to answer that question. I want us to consider the shape of the distribution or the data set that we're working with. And we've talked about in class a couple different shapes. We've talked about symmetric distributions. And so you can see the symmetric curve is spinning into play right now. Now I've gone and got my pen so I can write on this distribution, but here's the idea. In symmetric distributions, the mean, the median, and the mode are all located. That's supposed to be an arrow. All right, we're going to try the, I have a writing tablet over here. All are located right there in the center. Okay, now why? Well, for different reasons. If we think about this as being a graph from earlier in the chapter, we have a frequency or relative frequency axis here. Here are the values of x listed on this axis. So maybe these are your GPAs, or let's say your heights, because heights tend to be fairly symmetric. We have a curve that comes up, as you see, and then goes back down. So where would the mode occur? Well, the mode would occur at the most frequently occurring observation, and that's going to be at the peak. And you can see in a symmetric curve, the peak of the distribution is right about here. And so we're going to list that as the mode. So when you look at a curve, you go to the peak, and that's where you'll find the mode. The median is going to be the place, what we say, the middle of the ordered data, and we're going to judge that. Take a look at the area on either side of the median, and it should be the same. So we're going to try to locate a line in this curve that evens out the area, the number of the observations, or the area under the curve on either side of it. And in a symmetric curve, that's going to be, again, right here, smack dab in the middle. The mean is a tricky one. The mean is going to be the location in the curve where, if you could pull this curve off the board or off the screen right now, the mean is going to be at the location where it would balance. So where could you put your finger down here on the number line so that it would balance? Well, in a symmetric curve, the balance point, I'm going to try to draw a ton of arrows here just to make it really ugly for you guys, sorry. The balance point would be right there. If I tried to put my finger down here, for instance, and balance it, there'd be too much weight on the left-hand side and it would fall over. And so the balance point is how we're going to find the mean. And you're probably listening to me thinking, well, they're all the same place. Who really cares? And that's a good point until we get to this curve, until we get to skewed data. And again, we've talked about two different directions of skewness. And I'm supposed to have a picture. Here it is. And I jumped ahead here a little bit. Sorry about that. In skewed distributions, again, we have values of x on the number line. And I'm going to have to go get my pointer again. Let me get my pen. Values of x on the number line down here. The mode, we go to the peak. And the peak in this distribution is going to be right here. So there's the mode. However, if you look at the area below the mode, if you look at this area here, you can see that there's more area to the right. So that can't be the median. And so in order to even out the areas, I came over to this line right here and said, hey, you know what? Again, nice looking arrow there. I said that, at least to me, appears to be the point where the area to the left of that line and the area to the right of that line is about the same. But what you would find is if I tried to balance, I'm looking for the mean now, if I tried to put my finger right here, because of this long tail, the values of x that are out here in the tail, it wouldn't balance. And so the mean actually gets shifted further to the right. And you can see in your notes, I've drawn this arrow right here, which looks a lot nicer than some of the arrows I've drawn with the red pen. But this arrow right here indicates that the mean tends to chase after those big values of x. If I had a data set that was made up of the numbers 1, 3, and let me get an even nice number here, let's say 5. Let's put another 3 in here. Let's put another 3. So let's do this. 1, 3, 3, and 5. Well, the mode would be 3. The mean would be 3. If you added up those numbers, you get 12. You divide by 4, you get 3. And the median would be 3 as well. Now what happens if I make this a 50? Well, the mode's still 3, the median's still 3, but now you're taking 57 divided by 4. You're getting a much bigger number, and that's what tends to happen. The median and the mode are pretty unaffected by the extremely large values that you tend to see in a skewed distribution. But this 50 here counts. It gets added into. The mean looks at every single value, and this extremely large value tends to inflate, and that's why I draw this arrow over here. The mean tends to chase the extreme values in the distribution. The same thing would be true in a skewed left distribution. The mean would be way over on the left-hand side. But what I'm getting to is, because the mean is influenced so much by those extreme values, it's really not that great of a measure of center in a skewed distribution. And so the answer that I put here at the bottom of the page, which you guys have been watching or looking at for a while, in skewed data, we like the median. We say it's a better measure of center. In symmetric distributions, and everything I've said so far, you say, well, in symmetric distributions, it really shouldn't matter because look what we got up here. The mean, the median, and the mode, which is now hidden behind. Remember, the mode's right here, too. The mean, the median, and the mode are all at about the same value. Why would it matter? And it matters because of some things we're going to learn in Chapter 4. We'll get there. But we're going to say the mean is a better measure of center. While they all appear to be at the same spot, the mean is going to be more accurate. And so we like the mean as our measure of center when we're working with symmetric distributions. Now, I say all this knowing that we're going to work a lot more with the mean this semester than with the median. And so let's go on and talk about some other measures of center. We'll come back to that idea, but we're going to work with the mean a lot more. But the mean and the median are the two that you need to consider when working with measures of center. Now let's move ahead to measures of variation. And this, the idea I have now, and I'm going to come up to the top of the screen and draw this picture up here. And it doesn't allow me to keep the pen. Here's what I'm going to have. Let's talk about two distributions. One that looks like this, and another one that looks like this. Which one's more spread out? The first one I drew or the second one? Well, the first distribution, let's put them on number lines here, are more spread out. And I can even draw a picture where maybe the second one is drawn on top of the first one, not the best picture in the whole world, but you can see that the center of the distributions are about the same spot. Which one's more spread out? For lack of better terminology, let's say the tall skinny one or the shorter fatter one. Well, the short fat one has more variation in it. And so we want to look at some measures that will attempt to measure the spread of the distribution. And the first one we're going to look at is the variance. It's the sum of the squared deviations of the observations from the mean divided by n minus 1. Yeah, that's not any better probably. Well, this is the formula for the variance. And really what I want you to see, and again, I'll go get my pen. What I want you to see is right here. What this formula is saying. Remember, the x's are the observations themselves. This is your GPA or your height. This is the average of everybody. And just look at these two distributions I drew up over here. Let's call this one distribution A, the short fat one, the more spread out one, and B, the tall skinny one, is B. Think about where observations fall. Here's the mean. If we're talking about sample, this would be the symbol x bar. That's the mean right there. Think about distribution A. Look how far, look if there's an observation right here. Look how far that observation falls from the mean. Look how far this observation out here falls from the mean. The distances that you see, and that's really what this is, the sum of the squared, the deviations of the observations from the mean. How far the x's fall from the x bar. That's the key in the variance formula. Now, it just starts to get weird after that because not only are you looking at that distance, you're squaring it, you're summing up, you're doing a whole bunch of different stuff. But just think in terms of if distributions are not spread out, if they're pretty tightly packed. Look at this distribution here. Ooh, that's kind of a weird distribution. Most of the values of x fall close to the x bar value here. And so these distances that we see in this formula, the x minus x bar values, are going to be relatively small. That's what the variance is trying to measure. Now, a problem with the variance is it's measured in squared units. So if you're thinking about, say, your heights, your height, maybe I'm about 5'11", so I'm about 71 inches tall. Maybe the average is 65 inches. Well, I'm 6 inches above the mean when you consider both males and females. I'm 6 inches above the mean. Square that number. You get 36 squared inches. Squared inches. What the heck's a squared inch? If you're working with money, you work with squared dollars. So the variance, while it's a mathematically useful measure of variation, it's not a very practical, useful measure of variation. And so we go to the second one, and I'm probably going to have numbers. Hey, the numbers worked here. Standard deviation, the square root of the variance. Okay, so really, I say that we're going to say there's three measures of variation. There's the variance, there's the standard deviation. We're going to see the range here in a second. But really, two of those, the variance and the standard deviation, are tied together. The standard deviation is the square root of the variance. Now, what makes this useful for us, or why do we look at this? Because those squared units that we just talked about, those squared inches, those squared dollars, well, now they're the square root of that. They're back in terms of inches and dollars. And so the units of the standard deviation are going to be the same as the units of the problem. So if you're working with your height, you're working in inches again. If you're working with some kind of financial value, if you're working with stock prices, for instance, you're working with dollars again. So that's nice because I'm going to make up a word here. The standard deviation is interpretable. How do we interpret the standard deviation? Not so fast. Stay tuned. We're going to be looking at that in a second. We have a couple different methods of interpreting standard deviation. We have a couple different rules to look at. We'll get into those. We'll spend a fair amount of time in this video or the next video. But standard deviations are interpretable. The third measure of variation, and I guess I should have mentioned because I'm going to do some symbols here in a second, but standard deviations, when you're working with sample standard deviations, we saw the formula for variance. It was s squared. I should have mentioned this. That's a sample variance. The sample standard deviation, when you take the square root of s squared, you get s. Hopefully that makes sense to you. And so those are the symbols that we're going to use. The range is going to be much like the mode in that, while it's very simple to think about, the mode was the most frequently occurring observation. The range is the difference between the largest and the smallest observations. We don't use the range all that much. Now the range, I shouldn't disrespect the range quite that much because there are some places that we see the range used. Some of the graphing that we're going to do later in the semester with quality improvement, some of the things called control charts are going to use ranges. But in terms of measuring variation in data sets, if you take a difference between the largest and the smallest observations, well, it kind of makes sense. The further they are apart, the more spread out they are. It's not the most accurate or the best measure of variation, so we're not going to use it all that much. And so when we ask the question now, which measure is best, we have an answer, the standard deviation. And the answer that we give, the standard deviation, is primarily because it's interpretable. We're going to get some information. We get some useful knowledge concerning the shape of the distribution from the standard deviation. Again, we haven't looked at that yet, but we'll talk about that in a bit. Before we do that, however, I wanted to have one place in your notes where most, if not all, of the symbols we're going to see this semester are collected. And this is the way I'm going to do it. We have different symbols determined or based on whether we have populations or samples, and then we've looked at various categories. For instance, the mean, we said the population mean is the Greek symbol mu. The the sample mean is x bar. For medians, we said it's the Greek letter eta. The sample mean, or the sample median that we're going to use this semester is the symbol we're going to see is m. We don't have modes, so the next one I'm going to go to, kind of a weird way of saying this, but the number of things we're collecting, the number of experimental units. Well, if we use the entire population, the number of experimental units in the population is considered capital N. If you look back to the formula for the population mean, I took the sum of the x's over a capital N, and our sample size, that would be another way of saying this, the population size. Our sample size, the number of experimental units in a sample, is a lowercase n. So when I wrote the formula for the sample mean, it was the sum of the x's divided by the lowercase n. So this is just the different symbols we're going to use. Now typically, we just have sample values. And so we're going to have x bars and m's and n's. But we're going to use the x bar to estimate mu. We're going to use the median, the m, to estimate the eta. We work a lot with the x bar and the mu this semester. We don't work so much with the medians, as you'll see. So that's what I mean with the number of experimental units. The number of things we've collected, number of items collected, number of experimental units. All right, the variance. You've seen the formula for the sample variance. It's s squared. There's a similar formula. Doesn't involve an n. It involves a capital N for population variance. Again, we don't work with populations all that much, so I didn't even give you that formula, but it's similar, and it's the Greek letter sigma squared. Now this is the lowercase sigma. We saw the summation sign was a capital sigma. This is a lower sigma. I think statisticians long ago sat down and figured out what symbols can we use to cause the most problems, and this is what we've come up with. I don't want to make symbols a big deal in this class. I want you to understand what they are. We only use a handful of them, to be honest with you, but I do want to show you what they are. Standard deviations, take the square root of those values. S, we already saw that in the one sheet, and sigma. And so sigma is the standard deviation. It's a square root of the population variance, sigma squared. Data that we use, this one's kind of interesting because it doesn't matter if we're working with populations or samples. We consider the individual measurements, the individual observations themselves. Those are the x's. And so we'll use the symbol X to represent our data that we're collecting. And we've already talked about how we collect a bunch of X's, we form them to calculate an X bar, and we use it to estimate mu. And that's kind of a process we'll do later in the semester. The only other symbol, and we've seen and talked about each of these guys, the only other one I want to throw up here that we're going to need later in the semester is for a proportion, a population proportion. Now, earlier versions of this textbook, and just to date myself here a little bit, we're working in the 11th edition right now. I think when I first started teaching here at USF, we were on the 2nd or the 3rd edition. So I've been around the block a little bit. And one of the things that I've seen over the years is symbols have changed from one edition of the text to the next. The median symbol's changed, the population median and the sample median. But the symbol that changed that maybe I don't like as much is the proportion. Because when I look at these population values over here, I'm seeing a whole lot of Greek symbols. And in an old version of the text, the Greek letter pi was used here as a population proportion. And I was kind of a big fan of that. And P was actually the sample proportion. You see like an X and you see an S, and I like that. It's like Greek letters on this side, regular alphabet letters here on this side. Well, that's not what our book does anymore. We use P as a population proportion, and I really don't have a big problem with that. That's not a big deal. It's just a symbol, right? But here's the thing. Now we need a sample proportion. And so the symbol that's used, and you see this used, and when you move into your Stat 2 class, you're going to see it used quite a bit in statistics. When we go to estimate things, the estimate of P is P. We put a little caret over the top of it. And we say that's the estimate of the population proportion. This is going to be referred to as a sample proportion. But we don't read that as P caret, because that sounds weird. That's just who would use P caret. What we do use and what we do say is we call this P hat, because that's not weird at all, apparently. And obviously I'm hopefully joking here. P hat. That's what we're going to use. Now we'll see proportions when we get to the binomial in chapter 4 a couple weeks from now. But those are the symbols we're going to use. Now, the main reason I gave you it here is to put all our symbols in one spot. I'm not going to go crazy with formulas this semester. I'm not going to go crazy with symbols. But it is helpful when you see a symbol to have an understanding of what it is that we're working with. So if you see a sigma squared, you know that that's a population variance. If you see an X bar, you know that's a sample mean. And so there you have your symbols. And our next step now, we've talked about measures of center. We've talked about measures of variation. Our next step is to interpret the standard deviation. Now, these videos that I create tend to work better when I keep them a little shorter. So what I'm going to do is I'm going to stop this video right now, and I'll come back in another video and talk about interpreting the standard deviation. So long.